We've spent some time now looking at logarithms, but only in the sense of formulas. It also makes sense to look at their graphs because those are also a building block we're going to need going forward. The easiest way to get the graphs of the log functions is by remembering that inverse relationship, reflecting the graph of the exponential function that matches it along or across the y equals x line. So for example, if we draw the y equals x line on a standard xy graph, and we drew the graph of y equals 10 to the x, 10 to the 0 is 1, 10 to the 1 is 10, and then if we use negative values of x, we get fractions, and very quickly that drops off, like so. And so we get a graph that looks roughly like this. That's a graph that grows quite quickly as soon as we get past x equals 0. But we can see the relationship between that graph and the green line here, which is the graph of y equals log base 10 of x. They're simply reflections, where this graph goes through 1 and 10. This graph here, the inverse, goes through 10, 1. The y and x roles are reversed. In general, when we look at the properties of the log graph, we've mentioned this earlier, but the graph of log of x is only defined for positive x values. We can't even have a 0 value or negatives. But the range is all possible real numbers. If we took a careful look at this graph, it actually has an asymptote. It goes down forever. It never touches the axis, but it gets closer and closer. We can get any negative value we like. And even though the function is growing slowly, it never hits an asymptote. It's going to grow way, 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 way out, but it'll eventually get to any number that we care to reach. So again, just fundamental properties of the graphs are helpful to have. Only positive values can be put into a log function until you get to complex numbers, but that's not this course. And any number at all can come out of a logarithm. Just for practice, let's do the same kind of sketching for base 2 and base e. Y equals 2 to the x as our building block. We'd start at 1, and then when x is 1, we're going to get a value of 2. When x is 2, we're going to get a value of 2 squared, which is 4, and then it would go to 8, and so on. If we put negative values in, we would get 2 to the negative 1 is a half, and then a quarter, and then an eighth, and then a 16th. And so connecting those dots, we're going to get a graph like this, and its inverse. Let's put it in here, 2 to the x. And I'll keep the colors the same for the logarithmic version of it. We would have a mapping from here to here, here to here, a half, a quarter, an eighth, 16th, and 4, and so on. This graph would be the graph of y equals log base 2 of x. All right, last but not least, what about base e? The key for this is just to remember that e is a number. It is approximately 2.718. It's like pi, it does go on forever, but at least has a number that's close by. So at the end of the day, I usually think of it as a horrible approximation, but as e is around 3, a little less than 3. That allows us to do a quick sketch, because if we have y equals e to the x, let's do that here, then when x is 1, we're going to get a value a little bit under 3. When x is 2, you can take your calculator, and we get a value of about 7.4, which is off the chart here, say up here somewhere, and we can connect those dots. And we can also do some values, say at negative 1. We get a value of about 0.36, so under a half, so lower than the earlier graph. And we're going to see that same pattern bear out. It's always going to be below the y equals 2 to the x graph. So that's the graph of y equals e to the x, the natural base for exponentials. And then the inverse function has all the same properties we talked about. We take the points and we reflect them across the y equals x line. We'd get out to about 7 point something here at 2. We'd be down here a little bit below. And so it's going to have a stronger vertical asymptote and going to grow more slowly than the log base 2 function. And that's simply how we can get the shape as well as some of the details of logarithmic graphs. Notice the commonalities here again. There is a vertical asymptote. These are only defined for positive x values. They both go through this point here by default unless they're shifted or scaled, and they both have this slow growth shape. Once you get past the initial asymptote, they do grow forever, but very, very slowly.